Okay, this lesson is on dehydrating alcohols, which is a type of reaction called an elimination reaction. This is an elimination reaction, and it's called an elimination reaction because a small molecule, in this case water, is eliminated from the alcohol molecule. So you can call it either dehydrating, because that's removing water, or eliminating a water molecule. It's the same thing. Okay, so we're going to do two things in this lesson. We're going to look at how to dehydrate an alcohol, which is the elimination reaction mechanism. We'll have a look at that in detail, a couple of examples of that, and also an alternative way, which is decomposition, thermal decomposition. Thermal decomposition is an alternative way of eliminating a water molecule from an alcohol. Then we'll have a look at how to purify the product, which is distillation, and then separation, which is a required practical. So we'll be doing that in more detail in class. Okay, so let's start off with dehydrating, or the elimination reaction mechanism. So when we dehydrate alcohols, we actually make alkenes, which is quite handy. Let's just have a look at the general formula. So if we start off with the general formula of an alcohol, that's an alcohol, general alcohol. All right, and when we make it into an alkene, the general formula there is CnH2n. And we're going to eliminate a little water molecule there, like so. So these are alkenes, and this is a way of making alkenes from a renewable source, because our alcohols we can get from sugars, which we can make using photosynthesis. So you photosynthesize, you grow some plants, and you get the sugars out of them. You can ferment those into alcohols, and so then dehydrate them into alkenes. So when we've burnt all our oil and we still want to make some plastics, this is a alternative way of making our plastics. Okay, so that said, let's have a look at the reaction mechanism. This is just as a reminder, this is the elimination reaction mechanism. And to look at that, let's have a look at an actual reaction. Let's start off with ethanol. So let's write out ethanol, slightly shortened fashion. CH3CH2, and that's going to be bonded to an oxygen hydrogen, and remember the oxygen's got a couple of lone pairs on it, and we're going to use a sulfuric acid catalyst. So it's acid catalyzed elimination reaction. We're going to make ethene, which is CH2 CH2, and a little water molecule gets eliminated. So let's have a look at the mechanism. If we remember, this is delta minus, this is delta positive. All right, and so when we find a little hydrogen ion that's floating around from the catalyst, one of these lone pairs is going to attack it and make a bond with it. And so what that does is it makes an intermediary product. Let's go back to blue and draw out an intermediary product. So we've got our CH3 is not very interesting, so we'll just write those like that. But now we have an oxygen that has 3 bonds to it. So let's just track the electrons. Let's go to red and mark these, these electrons here. All right, the ones that attack the hydrogen ion, and they're going to make this bond here. And this hydrogen that I've just underlined in red is that one there. All right, and So of course this oxygen now has essentially donated one of its electrons to the hydrogen, and therefore has a +1 formal charge. And so what it then does, of course, is it draws the electrons. Let's change to green. It's going to draw these electrons towards itself. Okay, so it's going to draw those electrons towards itself, so much so that it's going to break off. And that water molecule is going to break off and go. So let's draw that out. So let's draw it over here. So again, we've first got our CH3. In fact, let's draw it out. Let's draw it out fully. So I've got CH3. Draw those hydrogens in. CH2. Okay, and those green electrons have gone now. So that one of those green electrons was this carbon's, right? So that leaves that carbon as with the +1 formal charge, and the water molecule has gone. So we can just write that in there like that. And now the thing is that carbon is more electronegative than hydrogen in the first place, and what's more, we have a carbocation there, which means that the carbon is even more in need of an electron than it was before. So one of these hydrogens that is associated with the methyl group that is going to provide the electrons. And so let's take this bottom hydrogen. Those electrons are going to be drawn off, and they're going to make that bond there. And so this carbocation becomes like this. And let's just track our electrons. All right, in red, they were those two electrons, which have now become this pi bond here. And that's left this hydrogen here without an electron, and so it leaves as a proton, thus regenerating the catalyst that we started off with. And so now we have regenerated our catalyst, our hydrogen ion. We've got our ethene as a product, and we've eliminated a water molecule, which is all consistent with this reaction at the top. So let's have a look at elimination reactions in firstly symmetrical and then unsymmetrical alcohols, because with the unsymmetrical alcohols we might get some EZ isomers. Okay, let's start off looking at symmetrical alcohols. Let's take propantool. Let's draw propantool out. So there we are. Have patience while I draw in all these hydrogens. And the middle carbon is the number 2 carbon, and so that's because it's propantool. We're going to have the hydroxyl group on that middle carbon there, and this reaction can go two different ways. Let's just draw out our lone pairs on this oxygen there, and as you remember, it's acid catalyzed, and so this lone pair could attack a hydrogen ion that's floating by. When it does so, it's going to make the intermediate product. Let's draw that up. Okay, so just imagine hydrogens on all the ends of those bonds there, and let's not forget that now our oxygen is going to have a +1 formal charge, so then we're going to draw those electrons off, and we're going to make the carbocation and the water molecule. Let's draw those out again. Just draw the water molecule off down there, and put our +1 formal charge on the carbocation now, because those electrons have gone. It used to be, one of them used to be the carbons, now it's gone. And so the next step, in fact, for this case, let's draw in some hydrogens, because what could happen is we could either, let's take one colour, let's take green, we could either lose this hydrogen that I'm underlining in green. We could either lose that hydrogen as a hydrogen ion and take its electrons to make a double bond in the position that I've indicated there in green, or let's take purple, and it could equally easily be the other side. So it could be this hydrogen atom that provides its electrons in that bond there. So moving across to green, if it happens to be that carbon, let's draw out what we get. So we would get so this is propene, and you can call it propanine if you want. Alright, now let's switch to purple and do the alternative reaction. So you would then have your CH3 group bonded to your CH group. And your double bond becomes this one with our two hydrogens there. And as it happens, this would be also propene or propanine. And you can see the green propanine is the same as the purple propanine, and they produce one product. So that's what happens when you've got symmetrical alcohols to start with. However, that's not what happens when we start with unsymmetrical alcohols. So let's have a look at an example of that. Let's start off with butan-2-ol. So 4 carbons. It's butan-2-ol, so we're going to have our hydroxyl group there, and we can have a bunch of hydrogens everywhere else. Okay, let's draw in our lone pairs. One of these lone pairs attacks a wandering hydrogen ion, and so let's draw the next step. +1 formal charge has gone onto the oxygen. Let's leave the hydrogens off, save a little bit of time. So next, of course, the electrons that are in this bond gravitate towards the oxygen, and that becomes a good leaving group, so the water molecule leaves. So let's draw our intermediary. Let's draw our carbocation down here. So I've got 1, 2, 3, 4, and let's put our +1 formal charge in red. still got CH3, still got a bunch of other hydrogens there, and our water molecule has now gone. So now let's this time draw our hydrogens in, because this is the bit that hydrogen gets involved. Okay, so we could have, choose blue again, you could have this hydrogen that that gets eliminated, right? So this pair of electrons is going to come across here to neutralize the charge on the carbocation. And if that happens, let's draw that out in blue here. So we would have CH2, that double bond, that one there. You'd have a carbon hydrogen. Let's put these hydrogens in and save us writing all that out. Let's put C2H5 in like that. Okay, alternatively, let's let's use this hydrogen here. All right, and those two electrons there are the ones that go to neutralize the carbocation, making a double bond there. So in that case, you would have this. You would have so you have a CH3 group, then your carbon, then your double bond, then your carbon, then another CH3 group there. Alright, but we could also draw that two different ways depending on if a different hydrogen goes. Less in green, say if this hydrogen goes, you would also get an alternative product here. So you would have and let me just draw this out a bit more clearly, this purple one. You could more appropriately draw this one out like this. And you see you've got the EZ isomers here. So this would be the Z isomer, this would be the E isomer, and these EZ isomers are isomers of butene. And our original blue one is it's actually but1ene, isn't it? So you can see we get three different products from the unsymmetrical alcohol starting point. So that was how to dehydrate an alcohol using an elimination reaction. What we're also going to have a quick look at is how to dehydrate an alcohol using thermal decomposition. And you'll have come across thermal decomposition before. So we take the alcohol, in this case it's ethanol, put it in a boiling tube with a delivery tube connected up to it, and so we're going to heat it, and we're also going to introduce a catalyst, which is quite often aluminium oxide, and as the hot ethanol passes over the aluminium oxide, it breaks down into our ethene and a water molecule. And so along here comes our ethene and our water molecule, and as they bubble up through the water, of course the water condenses and just mixes in with the rest of the water, leaving our ethene to collect in the top of the collection tube there. And so we can dehydrate the alcohol using heat as well. So now let's move on to purifying the product, and we're really talking about the product of the elimination reaction. And the products of the elimination reaction are the alcohol and the water and any unreacted well, the unreacted alcohols. But so the product is in fact not the alcohol, of course it's the alkene. So the reaction mixture we're going to have in this round bottom flask. So that's the reaction mixture, which will be the alcohol and the acid catalyst. Let's write it out. So it could be sulfuric acid or phosphoric acid or a mixture of the two. And then you're going to heat it and it's going to react. And in fact, let's put a big cross, let's put a big black cross, in fact, through the Bunsen burner, because we've got very flammable reactants and products here. So we wouldn't actually use a Bunsen burner, even if we've got a gauze there. We would use a water bath or electric water heater, heater. Nevertheless, we're going to heat the reaction mixture and we're going to get these products. We're going to have an alkene, we're going to have some water that's been eliminated, and we're going to have some unreacted reactants there. And fortunately, they have different boiling points. And so what you're going to do is you're going to have a thermometer in here and you're going to heat it up until it gets to the boiling point of the alkene. All right, in which case the alkene is going to boil off and come off down here. You've got some, you're going to put water in here, and water's going to come out the other tube. And by the time your alkene gets down the condensing jacket, right, it's going to condense into a liquid and drip out into your beaker or your conical flask. But of course, unless your boiling point of your alkene, say it's about 80 degrees C, you're still going to get some water coming off with your alkene, and so your product that you're going to collect here is going to be impure. That's going to be impure product, and so what you're going to have to do is you're going to have to separate as much as you can your product from the impurities. So let's have a look at the next slide here. And this bit of apparatus that we've got here is got we call a separating funnel. And it's got a useful tap on it. Okay, and it's generally used to separate immiscible liquids, mixtures of immiscible liquids. And in this case, our alkene is likely to be on top, and our water and our water soluble impurities will be on the bottom. So our water is produced in the elimination reaction, of course, and we won't have reacted all of our alcohol. Right, so, and alcohols are soluble in water, so they would mostly be in that lower liquid. Okay, so what you can do is you can run the tap out, you can open the tap and your water and water soluble impurities would run out first, and you can collect those. And when you get down to about here, just short of the borderline, you would stop and then run it out into a separate beaker until you've just started running your alkene out there. And that would be waste, because you'd probably throw that away. You wouldn't do anything with that. And then the third little collection vessel you would use to collect your alkene, and that would be how you would collect your relatively pure product, your alkene. It's not going to be totally pure, it's still going to have some water in it. So you might add some calcium chloride to it, which is a drying agent, and that removes any more traces of of water. And you might even want to do a further step, which would be to distill it again, which would make it very pure. And once you've gone through all those steps, you've got some pretty pure alkene. So let's finish off by reviewing what we've done. We've looked at two ways of dehydrating an alcohol. We've looked at elimination reactions, and we've also looked at symmetrical and asymmetrical alcohol starting points. And we've also looked at using heat as well for thermal decomposition, and we've purified our product of our elimination reaction, first of all by using distillation, and then followed by a separating funnel to separate the two immiscible liquids. And that practical in the second half of the video is we're going to do that in class anyway.